Hello Gen Chem students. So today this is my video on combustion analysis, but first a little background information. So whenever we've been drawing molecules, just some examples, CH4, H2O2, when we give a formula for something that we want to draw or something we want to know something about, we give a molecular formula, which is just simply the number of atoms in each molecule, and this is something that's used everywhere. However, some experiments that we do with samples don't tell us the exact number of atoms in one molecule. They give us instead something else. They give us the smallest whole number ratio of atoms. So this is something called an empirical formula. So let's just pick an example, H2O2. That is its molecular formula. But we could simplify this to the smallest whole number ratio. And this HO would be the simplest ratio, and this would be the empirical formula for this molecule, which happens to be hydrogen peroxide. So first let's get just a little more understanding and practice with empirical formulas. Here are three molecules. So first of all, hexane, its molecular formula, the number of atoms in each molecule would be C6H14. So now this, to make it the most simple ratio that we can in the empirical formula, these are both even numbers, we can divide them both by 2. So we have C3H7. So that we can't divide any further to get only whole numbers. So this, C3H7, is the empirical formula for this molecule hexane. Glucose, you can see it here, some very simple and very ubiquitous molecule. Its molecular formula, C6H12O6. So in one molecule of glucose we have this many types of each atom. But again, this isn't the simplest ratio. The empirical formula, the simplest ratio, so now we can actually divide everything here by 6. So we can have CH2O. So that is the simplest ratio, that we have twice as many hydrogens as we do carbons and oxygens. And now caffeine here, which is a very wonderful molecule, I'm told. I don't use it personally, but C8H10N4O2. That is its actual molecular formula, the number of atoms in one molecule. And this, we can further simplify it. We can divide everything by 2 here. C4H5N2O. So this would be the empirical formula, the simplest whole number ratio of each of the different types of atoms in caffeine. So that's empirical formulas. Another type of background information we need now is something about combustion reactions. So combustion reactions are a type of redox reaction where we have oxidation numbers changing between the reactants and the products. Almost always oxygen gas is going to be a reactant, and typically a combustion reaction is an exothermic reaction that releases heat, and it's commonly thought of as burning. So whenever we burn something, we need oxygen to be able to do that. If we can cut off the supply of oxygen, then the combustion reaction will stop. It will use up all the oxygen present and stop the fire, stop the burning reaction. Here are two different examples of combustion reactions. One of them, this is Sc, scandium metal. It's reacting with oxygen gas to produce the product scandium oxide. This type of reaction is a combustion reaction. It is a redox reaction. You can see that scandium is being oxidized. This type of reaction, though, it does release heat, but it actually happens very slowly, so we don't see any kind of burning. And this, when it happens very slowly and we don't see any burning, when this type of reaction happens, it is usually called oxidation or something called corrosion or rust. Especially when it happens to iron, this process is called rusting. Here is another kind of combustion reaction. Here we have a reactant which is composed of carbon, hydrogen, and oxygen. This happens to be acetone and some types of nail polish remover. It's reacting with oxygen gas to produce carbon dioxide, and water vapor. This is a very common type of combustion reaction, and that's the type that we're going to see in the application of combustion reactions we're going to do, which is combustion analysis, where the products are carbon dioxide and water. This is also the type of combustion reaction that we most commonly see whenever there's something being burned, or especially in like an internal combustion engine, anything in a car or bus, or even an airplane engine, we're combusting some kind of fuel with oxygen. We do combustion analysis reactions on samples that we want to know a little bit about. So here we have some generic reactant, but it does contain carbon, hydrogen, and oxygen. It's in the gas phase, and it reacts with oxygen gas to produce carbon dioxide and water products. So this reactant, we don't really know what it is. It's some kind of unknown sample we want to measure, but we do know it contains carbon and hydrogen and oxygen. If we combust this, we first weigh it out and know exactly how much we burned. Then we recover the amount of carbon dioxide and water vapor that are produced from this reaction. And these are the three different pieces of information that we need. And what we're going to do with them is, if we have grams of CO2 here, we can use stoichiometry to then calculate the number of grams and moles of the carbon in the reactant, the original sample. Then we can do the same here for hydrogen. We can use stoichiometry to calculate back to the hydrogen in the reactant. So all of the carbon in the carbon dioxide came from the reactant. All of the hydrogen in the water came from the reactant. Now oxygen, though, we had an extra source of that here, oxygen gas. So what we need to do to calculate how much oxygen was in the original is we'll take that original mass, we'll then subtract the grams of carbon that we found and the grams of hydrogen to get this grams of oxygen. Now we'll use this to determine an empirical formula, the smallest whole number ratio of moles of carbon and hydrogen and oxygen. So now I'm going to go over two examples of this combustion analysis. Here's our first unknown sample. We have a certain amount of it that we weigh out before combustion, and we recover a certain amount of water and CO2 and want to determine the empirical formula. So first I'm going to start with the carbon dioxide. We have the 33.27 milligrams of CO2. And we want to get to now moles of not carbon dioxide, but moles of carbon only. So here we'll have milligrams. I'm first going to convert it into grams. Now we have grams. This is grams of CO2. We need to convert it into moles. So CO2 is 44 grams approximately for 1 mole. And now that we have moles of CO2, we need to find moles of carbon, though. And this is exceedingly simple. For 1 mole of CO2, because of the formula, there's 1 mole of carbon. There's only 1 carbon in CO2. This then gives us a number of moles of carbon. This is the moles of carbon in original. Back in the product now, or sorry, back in the reactant. Moles of carbon in the reactant. So here we can see in our problem, we're given numbers with all 4 significant figures. So here in my answer, I'm actually giving 5. This is an intermediate step, and I want to use a lot of significant figures so that I have some place to round to. So we need to find moles of carbon. We also need to find grams of carbon. So carbon is 12 grams per mole. And then this works out to give us grams of carbon. And our original is in milligrams, so I'm just going to go ahead and convert this into milligrams as well. Milligrams of carbon. So our original sample had this many moles of carbon, this many grams, this many milligrams of carbon in that original reactant sample that was combusted. Now we need to do this same process but with the water product. So for water, we had this 20.42 milligrams of water. Again, convert that into grams. And now we have grams of water. We need to convert that into moles. So water is approximately 18 grams per mole. And now we have moles of water, but we need instead moles of hydrogen. So if we had 1 mole of H2O, just from the formula, we have 2 moles of hydrogen. So this works out to give us 0.22689 moles of hydrogen in the reactant in that original sample. So now we need to know the number of grams of hydrogen as well. So hydrogen is actually just 1 gram per mole approximately. So this gives us the exact same number of grams of hydrogen. And we can convert this also into milligrams. Milligrams of hydrogen. So now we have moles and grams, milligrams of hydrogen in the reactant. So what we have now is we need to determine now something about the oxygen present. So we have our original, the reactant, and all we know about it is its mass, 23.46 milligrams. So what we do know about it is the carbon, how much carbon was made up in the, we know how much carbon was in that original sample. It was this in milligrams, 736 milligrams. We also know how much hydrogen was in that original sample, which was the 2.2 some milligrams. So their original contained only carbon, hydrogen, and oxygen. So whatever is left over has to be milligrams of oxygen, which works out to be 12.1175 milligrams of oxygen. So with this, we know how much oxygen was in that original sample. What we need to do next is determine an empirical formula, the smallest molar ratio. So we need moles of oxygen as well. So we're going to go from milligrams into grams. And now from grams to moles. Now we have this. So now we have moles of oxygen in the original, as well as the moles of carbon and moles of hydrogen that we calculated previously. Now we need to use that to determine an empirical formula. the smallest ratio, smallest whole number ratio. So we have carbon, which was the moles of carbon. We have hydrogen. And now oxygen. So this is all that we need to determine a empirical formula. What we're going to do is take the others and divide them by the smallest number of moles, and put that in the denominator, the other two in the numerator at different times. So this happens to be carbon. It's just a little bit smaller than the others. So first let's take the hydrogen to carbon. And this works out to be 3.0006. Super, super close to 3, so we round to 3 exactly. And the other one, let's take oxygen on top now. Divided by the carbon. And this works out to be really, really, really close to 1. So now we have a ratio of carbon and oxygen is 1. There's the same number of carbons as there is of oxygens. And then for between carbon and hydrogen, the ratio is 3. There's 3 times as many hydrogens as oxygens. So CHO. Carbon is 1 because it was in the denominator here, was the smallest. We know there's the same number of carbons and oxygens there, and for hydrogen it's 3. So what we have for our empirical formula is CH3O. That's it. Okay, great. So now with our empirical formula, of CH3O, we can start to think about what molecular formulas are possible. So for this, we need to just keep this ratio intact, but we can multiply it by anything. So if we multiply this by 1, we'll just have CH3O. We could have a molecule composed of just 3 hydrogens, 1 carbon, 1 oxygen. Well, we could also have any multiple of that. Let's say we multiplied everything by 3. We would have 3 carbons, have 9 hydrogens, and 3 oxygens. So this would be another possible molecular formula. It would keep the same ratio, the same empirical formula though. We could also maybe multiply it by 20, anything like that. All the empirical formula tells us is the ratio. Okay, I'm going to do one more question here about combustion analysis and determining an empirical formula. So here we have another molecule R. We know how much was combusted, and then we know how much of the 2 different products were made, CO2 and H2O, to determine an empirical formula for those. Okay, let's start with the CO2. So that's how much was made how much product CO2 was made. So in this case we have grams. So we're going to go from this to moles. That's moles of CO2. And now if we had 1 mole of CO2, we'll have 1 mole of carbon because of the formula. So that works out to give us just shy of 0.018 moles of carbon in that original sample. Then we need to know something about the grams as well. So we're going to multiply that by 12 grams per mole of carbon, again rounding just a little bit to give us this 0.21578 grams of carbon. So that's moles of carbon and grams of carbon in that original sample that was combusted. Now let's do the same for the water. So we have this 0.2719 grams of H2O that was produced in the combustion reaction. 18 grams per 1 mole. And if we had 1 mole of H2O, we'll have 2 moles of hydrogen. So then that gives us this. We have some moles of hydrogen that were in that original sample. And then because hydrogen is 1 gram per mole, we have the same number of grams in that original sample. So our original was the 0.4380 grams. We're going to subtract that from the grams of carbon that we found just before, which was the 0.215 grams of carbon, minus the grams of hydrogen now that we just found. And I'll just punt this to the next slide. And that works out to be, with the rounding, grams of oxygen. So now we need to convert this into moles. Oxygen is 16 grams per 1 mole. And we have 0.012 moles of oxygen. Okay, so now to determine the empirical formula, we need the number of moles of everything. So we have this. Moles of carbon. Moles of hydrogen. And now moles of oxygen. And whatever we do, we'll need to figure out the smallest one and then take everything and divide it by that smallest one. And that in this case is oxygen. So we have first, let's just take the moles of hydrogen and oxygen. So this, it works out to be 2.5 some. Very, very close to 2.5. And the other one, carbon and oxygen. This one, it works out to be about 1.49 something. Again, very, very close to 1.5. So for our empirical formula, oxygen was in the denominator, so it's going to be 1. Between carbon and oxygen, we've got 1.5. And between oxygen and hydrogen, we've got 2.5. So what we have now is something that's not a whole number ratio. Our empirical formula does need to be a whole number ratio. So this, we're going to have to multiply it to get an empirical formula that's a whole number ratio. So we can just start multiplying it by something. I'll just start with 2. And this will give us C3H5O2. And now we do have a whole number ratio. So our empirical formula for compound R, or molecule R, is this C3H5O2. So that is the simplest whole number ratio of each of the different types of atoms in molecule R. Okay, so that's the end of the video on combustion analysis. Thanks for watching, and I'll see you in class.